All right, so in this lesson, we are going to be talking about a special kind of log called the natural log. And the natural log connects to a special number that we call e, and we're going to talk more about that, but that's the base e and its connection to that natural log. And we're going to use those to solve equations. We're going to use the same processes that we've been using to solve log equations. The rules still apply and the properties still apply, but now we're going to look at it with this natural log situation. So as we work through this lesson, I want you to be thinking about your essential question. When taking the log of e, so that base e, that special number, what does that turn into? So when I take the log of e, just like I take the log of 4, what does that turn into? All right, so we just have some definitions and some information that you need to get in your notes. So first we're going to talk about what is e. We're going to talk about that base e, and then as an exponential function, and then as a logarithmic function. All right, so first of all, e is a special number. It's an irrational number, meaning it goes on and on and on and it doesn't repeat. So it's like pi. And it has an approximate value of 2.718282 ... goes on forever. So just like pi is 3.14159 ... E is that same kind of idea. It's this number that we use in math. It often occurs as the base of an exponential and a logarithmic function, and we use it in real-world scenarios that we'll talk about later. So just a couple things you need to know as base e in an exponential function and base e as a logarithmic function. So first of all, we call these a natural base. So exponential functions with that base e we call a natural base. This is what it would look like is the function. So f of x is e to the x. So e is the base, and then my exponent is that x value or that input value. As a logarithmic function, we call them a natural log. And it would be written like this: f of x equals log base e of x. And then we can abbreviate it as f of x equals the ln, which is the natural log, and you have that button on your calculator of x. So the biggest thing that you really need to know is that these are interchangeable. So if I have log base e of a value, an input value, I can rewrite that exact same expression. So I can replace the log base e with natural log of x. We don't have a function on our calculator that is log base e, but we do have that natural log function on our calculator. So that is the biggest thing that you need to take away from this screen. All right, so the first thing we're going to do is we're just going to work through converting between the forms. So how do I go from base e to the natural log, and then how do I go from the natural log to base e? So we're going to start with 1, 2, and 3. E to the x equals 24. So remember back to when we first started talking about logs, I have my base to my exponent equals a value. So when I want to write that in log form, I simply say log base, whatever it's equal to, equals the exponent. So if you remember that, so I'm going to rewrite number 1 in log form. So if you remember, we say log base, whatever the base is, and in this case it's e, of what it's equal to, so 24 equals the exponent. So log base e of 24 equals x. And if you remember, I said pay attention, anytime that I have log base e, it's interchangeable with that natural log. So I can rewrite this as the natural log of 24 equals x. So all I did was I simply took it out of exponential form into log form using what we've been doing for the last week and a half. And then I replaced that idea of log base e because I know log base e is the natural log. So I simply replaced that with the natural log of 24 equals x, and that's my answer. All right, so let's look at number 2. E to the 9 equals x. So the first thing I'm going to do is I'm going to put it in log form. So I have log base e of x equals 9. And I noticed that I have log base e, which is interchangeable with that natural log. So I'm going to rewrite it as the natural log of x equals 9. So you might be wondering why we're doing this, and the reason is, as we talked about, is I, for instance, can type this into the calculator. I don't have a log base e function on my calculator, but I do have a natural log, and since they're interchangeable, I could literally type into my calculator ln, which is over on that left-hand side, of 24 and hit equal, and that will tell me what x equals. All right, so go ahead and pause the video, and I'd like you to rewrite this in log form first. If you can take it all the way to the natural log, that's fine, but just start with that log form first. All right, so hopefully you were able to get that log base e of 72 equals that exponent, so x plus 5. So then go ahead and put it all the way into the natural log form. You don't need to solve for x or anything. We're just rewriting it into that natural log form. All right, so that would be the natural log of 72 equals x plus 5. All right, so that's going from base e to natural log form. So now we're going to work our way backwards, and we're going to go from the natural log form to the base e form. So I noticed that I have the natural log of x equals 58. All right, so when I think about the way that I went before is I took the base e, because we essentially want this to end up looking like this. So the route that we took was we took base e, we put it into log base e form, and then we were able to take that log base e and turn it into the natural log. So now we're going to move backwards. So we essentially want to rewrite this as log base e because those are interchangeable. So the first thing I'm going to do is I'm going to take this natural log and I'm going to replace it with log base e. So I end up with, like I said, log base e of x equals 58 because these two things, the natural log of x and log base e of x, are interchangeable. So now that I have this, I'm going to go back and I'm going to put it into the exponential form. So this is the log form. So it's e to the 58 equals x. And that's my answer. All right, so let's go ahead and take number 5, the natural log of 6 equals x, and let's put it in that base e form. So the first thing we're going to do is we're going to have that conversion. We know the natural log of 6 is the same as log base e of 6. And then from there, I can take log base e of 6 equals x, and I can rewrite it into exponential form. So that gives me e to the x equals 6. All right, so go ahead and pause the video, and I'd like you to try number 6. Go from that natural log to the base e. Go as far as you can. If you can only get it to that next step, that's okay, but I'd like you to try this one on your own. You don't have to solve it. You're just rewriting it into base e format. All right, so hopefully you were able to get it to log base e of x minus 9, because that's interchangeable with that natural log, equals 32. And so from there, I take e, the base, to the power of 32, and that equals x minus 9. All right, so converting between forms is really important to be able to solve those equations because you're going to need to be able to recognize that the natural log of a value is the same as the log base e, which will then allow me to go between those two forms and solve these equations we're about to do. All right, so the last thing that I want to do before we actually start solving is I want to make sure that we can see the connection between those properties that we worked with before with just regular logs also apply to the properties of natural logs. So you don't have to learn a whole new set of properties. It's the exact same properties. We're just going to apply them to this natural log format. So number 7, I see the natural log of 3 plus the natural log of 16. So they share the same log, that natural log. So when I see addition, that's going to tell me that I can use multiplication to condense it. So I'm going to end up with condensing it to the natural log of 3 times 16. And then I can simply say 3 times 16 is 48. So this can also be written as the natural log of 48. Nothing new, just applying it to our natural log format. Exact same process though. All right, so number 8, the natural log of 63 minus 2 times the natural log of 3. So I see that they both share that natural log. One thing I need to get rid of first is this 2, so I'm going to use the power property to put it behind. So I'm going to rewrite that. All right, so I rewrote it as the natural log of 63 minus the natural log of 3 to the second because I use that power property. So now I notice that I have subtraction. And so in the properties, subtraction corresponds with division when they have the same log. So they both have that natural log. So I can rewrite this as the natural log of 63 over 9. And I got 9 because I simplified 3 squared. I could have rewritten it that as 3 squared. But I went ahead and skipped that step. So then my final thing is because I can simplify 63 over 9, I simply get natural log of 7. If you could go straight from, some of you might be able to go straight from this down to this, which is totally fine. If you can jump that step, that's okay. Just make sure you don't lose any details. All right, so number 9 looks a little tricky, but I think you can do it. So go ahead and pause the video and see if you can simplify using the properties. All right, so for this, I noticed that I had some numbers being multiplied out in front of the log, so I made those exponents. So I had the natural log of 64 to the 1/3 plus the natural log of x squared, because I simply moved those into the exponent position. And then I noticed that multiplication was happening, so I turned it, and they had the same base, so I turned it into the natural log of this value times the natural log of this value. And if you notice up here, we know 1/3 means it's taking a square root or cubed root or a fourth root, whatever that fraction, when there's a fraction. So 1/3 means it's the cubed root. So I'm thinking about what number times itself 3 times gives me 64. Well, I know 8 times 8 is 64, but that's the square root of 64. So the cubed root, I know that 4 times 4 times 4 gives me 64. So that's where I got that 4 from. And then x squared can't be simplified any further, and we know that when we're adding, that becomes multiplication when they have the same base, and so I simply rewrote it as the natural log of 4x squared. All right, so for number 10, we're going to now take a condensed log, and we're going to use the properties to expand it. So we're going through that process just in reverse. So I noticed that I have the natural log of 5x. And when a number and a variable are next to each other, they're being multiplied. And we know that multiplication connects to addition when they have the same log. So this is going to become the natural log of 5 plus the natural log of x. And that's as far as I can take it. All right, so number 11, I've got the natural log of a to the 3rd divided by b, all to the 2nd power. So there's a couple of ways you can approach this. I noticed that I have an exponent, and the power property says that I simply take that exponent and I put it out front. So I can take that second and put it out front to begin with, or I can distribute that second to everything on the inside. So a to the 3rd 2 times becomes a to the 6th. B to the 1st 2 times becomes b to the 2nd. So either way that you think about it, it doesn't matter. You're going to end up with the same answer. But just pay attention to those exponent rules that you learned in Algebra 1. If you approach it, you're going to end up with 6 times the natural log of a minus 2 times the natural log of b. And I'm going to explain either method. So over here, I chose to put the exponent out front first. So I brought that 2, and so I said 2 times the natural log of just what was already in there. So then I decided to use the division property, which says that's the same as 2 times the natural log of a to the 3rd minus 2 times the natural log of b. So I simply broke up the division, and I used that property to turn it into subtraction. Well, over here, I still have an exponent, so I use the power property again to bring that out front, and so 2 times 3 gives me 6. And then the rest of it just stays the same, so I have 6 times the natural log of a minus 2 times the natural log of b. Whereas the other method, which for some people might seem simpler, is to go ahead and distribute that squared. So this means a to the 3rd over b 2 times. So if I have a to the 3rd 2 times, that gives me a to the 6th. And if I have b 2 times, that gives me b to the 2nd. And then I applied the division property, and I said the natural log of what's on the top minus the natural log of what's on the bottom. And then I brought my exponents out front, and that still made me arrive at 6 times the natural log of a minus 2 times the natural log of b. All right, so let's look at number 12. Let's go ahead, and I'm going to get you going on the right path first with just a question. I want you to think about, how can I rewrite the cubed root so that it has an exponent? So just think about that for a second. How can I rewrite cubed root so that it's an exponent instead of the root sign? So hopefully you were able to remember that the cubed root is the same as anything being raised to the 3rd power, the 1/3 power, sorry. So I simply rewrote this as the natural log of what's on the inside of the cubed root, so m squared n, all to the 1/3 power. All right, so go ahead and pause the video. This one's a little tricky, but I want you to see if you can expand that whole expression using those properties to arrive at its expanded form. All right, so whichever method you chose, you should have ended up with 2/3 times the natural log of m plus 1/3 times the natural log of n. So I'm going to show you the two different methods using either whichever method you prefer. So the 1/3 taking it out front first would make this 1/3 times the natural log of what's on the inside, so m squared n. And then go ahead and recognizing that this is multiplication. So multiplication corresponds with addition. So it's this whole value of the first number plus this whole value of the second number. So that gives me 1/3 the natural log of m squared and then plus 1/3 the natural log of that n. And then I simply recognize that this one was fine, so it just came down, but this squared needed to come out to the front. So 1/3 times 2 is 2/3. And so that's how I ended up here. Or you could have gone the route of distributing that exponent. So the natural log and 1/3 times 2 is 2/3. So if I have m squared and I take a third of it, that would be 2 divided by 3. And then n to the first to the 1/3. So 1/3 times 1 is just 1/3. From there, I actually kind of skipped a step, but I essentially went straight from here to the answer. So I brought the 2/3 out front, and I did addition at the same time, and I brought the 1/3 out front. And so I ended up with 2/3 times the natural log of m plus 1/3 times the natural log of n. So the natural log and the base e is no different. We use the properties the same as we did with our other logs. All right, so if you notice, we're actually going to use the exact same questions that we used before when we were working with logs and solving equations. We're going to have two types. We have the type 1 where I have a log equals a log, and we're going to go through the same process. And then we're going to look at examples where I have a log equals a number, and we're going to go through those same questions. All right, so when I have a log equals a log, so if you notice in example 13, I have the natural log of this value equals the natural log of this value, and I'm going to solve. And remember to check for extraneous solutions, so I want to make sure, remember, logs can only be positive. So have I condensed each log? So when I look at it, do I have any values out front that need to be put as an exponent? Do I have any multiplication or division that I need to turn in, or I'm sorry, addition or subtraction that I need to turn into multiplication or division, which I don't. So this is as condensed as it can get because it's the natural log of one value equals the natural log of another value. There's nothing out front. What equation can I write and solve? Well, since they have the same log values, then I can simply set what they are the log of equal to each other. So that gives me 4x minus 27 equals 15 minus 2x. So I wrote the equation. Now what can I do to solve? Well, I'm going to bring minus 2x over here by adding 2x. And then I'm going to add 27 to this side. So when I simplify that, so that gives me 6x equals 42, and when I divide both sides by 6, I end up x equals 7. And I go back and double check, so I plug 7 in here, so 4 times 7 is 28 minus 27 gives me 1, and I plug 7 in here, so 15 minus 2 times 7, which is 14, is 1, so both of those are positive, so x equals 7 is a valid solution. All right, let's look at 14. So first question, can I condense the log? So I noticed that this log is as condensed as it can go because I have one natural log of this value. But over here, I have 2 times that natural log. So the first thing I'm going to do is I'm going to use the power property to rewrite it. And I'm going to get the natural log of k squared equals the natural log of 2k plus 15. So now that I have log equals log, what equation can I write and solve? Well, I can simply say that k squared equals 2k plus 15. So I need to solve it. I notice that k squared gives me quadratic. So to solve a quadratic, I'm going to set it equal to 0. So I'm going to subtract 2k and subtract 15. So I get k squared minus 2k minus 15 equals 0. So a is 1, so oftentimes I like to see if I can factor it. You can use the quadratic formula, you can use your graphing calculator, you can do whatever you want to get the solutions, but I think factoring is pretty straightforward because I'm looking for the factors of 15 that subtract to be 2, so 5 and 3, and I want it to be negative 2, so the minus sign is going to go with the 5. So that gives me k minus 5 times k plus 3 equals 0. So if I multiply two numbers together and their answer is 0, one of those numbers must be 0. So in this case, k would have to be 5, and in this case, k would have to be negative 3. Then I want to go back and make sure I check for extraneous solutions. So when I plug 5 in here, it's okay because 5 is positive, and 2 times 5 plus 15 is still a positive number. When I plug negative 3 in, I get 2 times negative 3, which is negative 6, plus 15 will still give me a positive number. However, when I plug negative 3 in for this k, it's going to give me a negative value, so I'm going to rule out that k can be negative 3, and it's simply k equals 5. All right, so in example 15, we've got the natural log of 72 minus the natural log of 4 equals the natural log of 6 times the natural log of the quantity a minus 2. So my first question is always, have I condensed the logs? So what I notice over here with this left side is I have subtraction. And then over here on the right side, I notice I have addition. So when I think about subtraction, I know that property when I'm condensing connects to division, and when I see addition, I know that property when I'm condensing connects to multiplication. So I'm going to rewrite this using those properties. All right, so I can rewrite that as the natural log of 72 over 4 equals the natural log of 6 times a minus 2. So I can go ahead and simplify 72 over 4, and that's 18. And I can simplify that 6. I can distribute that, and that becomes 6a minus 12. And since they are both 1 log equals 1 log, the equation that I can write becomes 18 equals 6a minus 12. And so then I simply solve this equation and I end up with a equals 5. And when I go back and check, the left side doesn't have any a value in there. So the right side, I have 5 minus 2, which is 3, so I can have the natural log of a positive number. So a equals 5 checks out. All right, what I'd like you to do is I'd like you to pause the video and try number 16 on your own. All right, so as you worked through number 16, hopefully you were able to get the m equals negative 2. If you got that, you can go ahead and move forward. If you didn't, I will explain it now. So the first thing that I saw is I needed to condense this squared and put it as the exponent. And so then I simplified m plus 4 squared became m squared plus 8m plus 16 because it's the same as m plus 4 times m plus 4. And that equals just the natural log of 4. So now that I have log equals log, I can simply say that those values are equal to each other. So I subtracted 4, which gave me 12, and then I factored it. You could use your calculator or the quadratic formula or whatever method. But the factors of 12 that add to be 8 are 6 and 2. And when I solved it out, I got m equals negative 6 and m equals negative 2. Now, when I plug negative 2 in, I still get a positive number, but when I plug negative 6 in, I get a negative number, and I cannot have the log of a negative number. So only negative 2 is my solution. All right, so now we're going to move into the second type where I have a log equals a number. These are the exact same questions and the same process that we go through before. It's just now we're going to be dealing with that natural log. And remember that the natural log is the same as base e, the log of base e. So keep that in mind as we work through these problems. All right, so for number 17, have I condensed and isolated each log? So when I look at this log is by itself, so I don't need to do anything. Like over here, if you notice, I have 2 logs, so I would need to condense it. All right, how can I write the equation in exponential form? So I'm going to take this and I'm going to turn it into its exponential form. So remember that the natural log is the same as the log base e. So I simply rewrite the natural log of 8x equals 2 as log base e of 8x equals 2. So now that I have that e, I can rewrite it into the exponential form. So base e to the second equals 8x. All right, so that gives me e to the second equals 8x. Well, here's the cool part is that e is a number. It represents that irrational number that's 2 point whatever. So in your calculator, if you notice, next to the 4, on the left of the 4, the natural log button has an e to the x that is in the blue. So if you hit second e to the x and put in 2, it's essentially taking 2 point whatever and it's squaring it. So it's going to give you a number close to 2 squared, 2 point whatever squared. So when you hit enter, I get 7.389056099 blah, blah, blah. So I actually can rewrite e squared because e is not just a variable, it's an actual value, just like pi is an actual value. So I'm going to rewrite that e squared as 7.3891. We're going to go to 4 decimal places. So I have 7.3891 equals 8x, and then I just have a simple algebra problem to solve by dividing by 8. That's a weird 8. And I end up with x equals 0.9236. So with this, you need to pay attention because I could see some people forgetting that e is an actual value. So if I ever have e to a certain exponent, that is a number that I can type into my calculator. So I want to go back and just double check that it's a valid solution. So 8 times a positive number is still going to stay positive, so we are good to go. All right, so let's look at example 18. So I have the natural log of x minus the natural log of 9 equals 7. So I'm in that type 2 situation where I have a log equals a number, but I need to condense that log because I have 2 logs and I need just 1 log. So I notice that the operation that's happening between those 2 logs is subtraction. So I'm going to turn that into division using the product property. All right, so that gives me the natural log of x over 9 equals 7 because that subtraction connects to division when I'm condensing. So now, how can I write the equation in exponential form? So I'm going to recall that the natural log is the same as log base e. So I'm simply going to rewrite this with log base e. And so I get log base e of x over 9 equals 7. So now I can write it in exponential form because I have my base of e. So e to the 7th equals x over 9. So then from there, remember that e is an actual number. So I can type into my calculator e to the 7th, and I get 1096.6632 equals x over 9. So to get x by itself, I need to undo divided by 9, so that's the same as multiplying by 9. So I'm going to multiply both sides by 9, and that will cancel. So I'm going to get a big number for this one. And I get x equals 9,869.6984. All right, so this process is no different than what we were doing. The only thing is needing to remember that the natural log and log base e are interchangeable and remembering that e is an actual value. So that's a number I can type into my calculator. So let's do some practice. All right, so with number 19, I have e to the x equals 57. So I can type e into my calculator. However, my variable, or what's missing, is the exponent. So I can't do that. But I can go ahead and use the idea that e connects to natural log. Because in my calculator, the same button that I use to type in e is the natural log button, which is simply like we use log. It's just a special kind of log. So what I'm going to do is I'm essentially going to work backwards. So I'm going to take e and I'm going to turn it into a natural log since my exponent is the variable. So in the previous examples, my variable has been on the other side of the equation. So now I'm going to take e and I'm going to rewrite it in the log form because I have the exponential, so I need to put it into the log form. So I get log base e of 57 equals x. So all I did was I turned that into the log form. So the base is e. And so now what I recognize is that log base e is interchangeable with the natural log. So I can rewrite that as the natural log of 57 equals x. Well, the good news is x is by itself, so in my calculator, I can just use the ln button, which is next to the 4, and type in 57, and I get 4.0431. And that is what x is equal to. All right, so let's look at 20. So I have e to the y plus 3 minus 6 equals 24. So have I condensed and isolated the log? So there's nothing I can condense because there's no multiplication or addition or subtraction. Now there is subtraction happening, but it is not e minus e. It's not a log minus a log. It's simply this log value minus 6. So I'm going to isolate by adding that 6 over here. I'm going to get all the constants to one side. So that gives me e to the y plus 3 equals 30. So I have a log equals a number. And so it's already in exponential form. So I'm going to put it into log form because my variable is in the exponent. So whenever my variable is what's equal to, that's when I'm putting it in exponential form because I want to isolate that variable. But when my variable is in the exponent, we use a log to solve those problems. So e to the y plus 3. So I'm going to rewrite it in log form. I'm going to take the log. So I get log base e of 30 equals y plus 3. So by taking that log, it ends up putting the exponent with the variable over on that side isolated. So now I remember that log base e is interchangeable with the natural log. So I have the natural log of 30 equals y plus 3. And so I can actually type in the natural log of 30 into my calculator. And so the natural log of 30 is 3.4012. And then I simply just subtract 3 from both sides. And I get that y is 0.401. All right, now it is your turn. So go ahead and pause the video, and I'd like you to try number 21 and number 22 on your own. Remember that e is a number, and that if I want to take the log base e, that's the same as the natural log. All right, so for 21, hopefully you were able to get that n equals 0.7361. And for 22, you were able to get that c equals 12.7377. So if you were really super close, it was probably a rounding error, so you've got the process. However, if you did not get those answers, I'll explain them now. If you did, you can go on to the wrap up of this lesson. All right, so for 21, the first thing I noticed is I had 5 times e to the 4n. So I need to isolate that log as much as I can. So by isolating, I divide by 5. So I simplify both sides by dividing by 5, and so I get e to the 4n equals 19. And so now I'm going to take the log. So log base e of 19 equals 4n. And then log base e can be simplified into the natural log. So the natural log of 19 equals 4n. And the natural log of 19 is something I can type into my calculator, and I get 2.9444. And I end up dividing that value by 4, and I get 0.07361. All right, so for 22, I needed to isolate the log. So in order to isolate that e, the first thing I did was I got rid of my plus 3 by subtracting 3, so I got 84. And then I isolated just the e. I always want to get down to just the e. So I divided by 2, and so I ended up with e to the c minus 9 equals 42. So when I get to that point, I'm going to take the log because my variable is in the exponent, and to get to that exponent, we take the log. So the log base e of 42 equals c minus 9. Log base e is interchangeable with the natural log, so I simply replace that. And then the natural log of 42 is 3.7377, and then I added that 9 to get the c by itself, and that's how I came up with that answer. All right, so what do we need to remember about solving equations with e or the natural log? So this is all the things we've been doing up to this point, except for we're applying it to that special situation with that natural log or that base e. So what are some mistakes you've made, or places where you've gotten to a point where you've stopped and didn't understand any further, couldn't go any further? What are those things that you're going to need to remember? What are those be sure to statements that you're going to need to refresh yourself on? Go ahead and pause the video and write those down in your notes. Have an interaction. All right, so what are 3 common mistakes you think students tend to make? What's your summary? So what have we done today? What is this lesson all about? And then can you rate your understanding for me? Good job, you guys.